Welcome back, everyone. We're kicking off another deep dive, and this time we're going to explore something pretty fundamental: the human eye and how we perceive this colorful world around us.
I'm excited to jump into this. It's one of those topics that seems simple at first glance, but the deeper you dig, the more amazing it gets.
Right. I mean, we use our eyes constantly, but how often do we actually stop to think about the incredible processes happening behind the scenes? It's like, how does this biological machine even work? From capturing light to sending signals to our brain that create those vivid images we see, it's mind-boggling.
It truly is. And it's something we often take for granted until, well, something goes wrong. But understanding how this intricate system works, it's not just about, scientific knowledge. It can really enhance your appreciation for the beauty and wonder of the world, like how we perceive color, depth, movement, all of that.
Okay, so let's break it down. Let's start with the anatomy of the eye, the basic structure. I remember learning about it in school, but a refresher never hurts.
Sure. Think of the eye as, well, kind of like a camera. A biological camera, of course. It has its own lens system, and just like a camera, it captures light and focuses it to form an image.
Right, a camera analogy, that's helpful.
Mhm.
So what are the key parts here?
Okay, so you have the cornea, that transparent outer layer at the front of your eye,
The cornea, yeah, I remember that.
and that acts as the first lens. The initial bending of light happens there.
Ah, so it's like the first stage of focusing.
Exactly. Then behind the pupil, you've got the crystalline lens. That's what does the fine tuning, allows you to switch focus between near and far objects.
Okay, two lenses working in tandem. And where does the light end up after passing through these lenses?
Well, it lands on the retina, that light-sensitive layer lining the back of the eye.
Ah, the retina. That's where the magic happens, right?
Pretty much. It's packed with these specialized cells called photoreceptors, rods, and cones. They're like tiny sensors that convert light energy into electrical signals.
So they translate light into something our brain can understand. Amazing.
Right. And those signals travel along the optic nerve all the way to the brain. And here's the really wild part. It's the brain that ultimately creates the image. It takes those electrical impulses and interprets them, not just as shapes and colors, but also depth, motion, all that good stuff.
So the world we see is basically a construction of our brains. That's kind of mind-blowing.
Hmm.
But how do our eyes manage to focus on things at different distances? Like if I'm reading a book and then look up at a plane flying overhead, how does that work?
That's where the power of accommodation comes in, the eye's ability to adjust its focus. And this is thanks to those ciliary muscles attached to the lens.
Ciliary muscles, okay.
Right. When you're looking at something far away, they relax, which stretches the lens thinner. That helps focus the light from distant objects. But when you look at something close up, like a book, those muscles contract, the lens thickens, and boom, you can see things up close.
So our eyes are constantly adjusting, even if we don't realize it. That's pretty impressive. But, sometimes our eyes don't focus perfectly. That's where things like nearsightedness and farsightedness come into play.
Yep, those are common refractive errors. They happen when the eye's focusing power isn't quite aligned with the length of the eyeball.
Right, so in myopia, or nearsightedness, distant objects look blurry. I remember struggling to see the chalkboard in school. That was probably myopia.
Could be. In myopia, the image focuses in front of the retina instead of on it, often because the eyeball is a bit too long or the cornea is too curved.
Ah, so the light converges too early. And what about farsightedness?
Hypermetropia, yeah. Opposite problem. The image focuses behind the retina, making close-up objects appear blurry. This often happens when the eyeball is a tad short or the cornea is too flat.
So it's all about where that light converges. And the good news is we have ways to correct these issues, like glasses and contacts. They might seem simple, but there's some cool science behind them.
For sure. To understand how those solutions work, we need to dig into how light interacts with different mediums, and that brings us to prisms. They're like these triangular pieces of glass that can really unlock the secrets of light.
Okay, prisms. I'm intrigued. What happens when light hits a prism?
Well, when light passes from air into a denser medium, like glass, it bends. That's refraction. And a prism's shape, with its angled surfaces, causes the light to deviate at a specific angle.
So it's not just bending, it's bending in a very precise way.
Exactly. That's different from just passing through a flat piece of glass where it bends but comes out parallel, just shifted a bit. With a prism, the light actually changes direction.
Fascinating. So how does this relate to our eyes in vision correction?
Well, remember how we talked about the eye focusing light? That's all about refraction, too. And glasses and contacts, they use lenses that are essentially like mini prisms, carefully shaped to adjust the way light enters the eye.
So they're redirecting the light to hit the retina just right.
That's it. Concave lenses spread the light out for nearsightedness, and convex lenses converge it for farsightedness.
So it's all about manipulating that path of light. Pretty ingenious. But prisms do more than just bend light, right? I remember something about splitting white light into colors.
You're thinking of dispersion. That's when white light, which is actually a mix of all colors, gets separated into its individual wavelengths because each color bends at a slightly different angle when passing through a prism.
Wait, so you're saying white light has all the colors hidden inside?
Yep. Think of a prism as a color decoder. It reveals the spectrum red, orange, yellow, green, blue, indigo, and violet. ROYGBV.
ROYGBV, the classic rainbow acronym. And speaking of rainbows, are those also created by prisms?
You bet. Rainbows are like nature's giant prisms. After a rainstorm, those tiny water droplets hanging in the air act just like prisms, dispersing sunlight and creating that beautiful arc of colors.
Wow, I never realized rainbows were basically large-scale prisms. That's amazing. So light can bend when passing through objects like prisms and water droplets, but does it also bend in other situations?
Oh, absolutely. It even bends as it travels through Earth's atmosphere. We call this atmospheric refraction, and it's responsible for some pretty cool visual effects.
Really? Like what?
Well, have you ever noticed how stars seem to twinkle?
Yeah, who hasn't? It's so captivating.
It's actually an illusion caused by atmospheric refraction. As starlight passes through those different layers of air with varying temperatures and densities, it gets bent and scattered a bit, making it appear to flicker.
So it's not the stars themselves twinkling, it's our atmosphere playing tricks on us.
Exactly. And atmospheric refraction also affects when we see the sun rise and set. We actually see the sun for a few minutes before it physically rises above the horizon and after it sets below it.
Wait, what? We're seeing the sun even when it's not technically there.
Yeah, because the light from the sun gets bent by the atmosphere. It's kind of like a mirage.
That's incredible. I never knew that. So it's not just prisms and water droplets. Even the air itself can bend light.
Exactly. And speaking of the air, that brings us to another fascinating aspect of light scattering. It's what makes the sky blue.
Oh yeah, the blue sky. That's something I've always wondered about. How does that work?
Well, it's all about how sunlight interacts with those tiny air molecules. When light hits them, it gets scattered in different directions.
Okay, scattering, got it. So why is the sky blue then?
Because shorter wavelengths of light, like blue and violet, are scattered more effectively than longer wavelengths, like red and orange. So when we look up at the sky, we're essentially seeing all that scattered blue light.
So it's not that the sky itself is blue, it's the scattered sunlight that we perceive as blue.
Precisely. And this also explains why sunsets often appear reddish-orange. As the sun dips lower, the light has to travel through more of the atmosphere, and more of that blue light gets scattered away, leaving those longer wavelengths, the reds and oranges, to dominate the sky. That makes sense. So those beautiful sunset colors are like the leftovers after the blue light has been scattered out. Amazing. It seems like there's so much more to light than we realize.
There definitely is. And we've only just scratched the surface. But before we dive even deeper, maybe it's a good time to recap what we've learned so far. What do you think?
Yeah, that sounds like a good plan. It feels like we've covered a lot of ground already.
All right. Let's quickly revisit some of the key ideas we've covered so far. We started by comparing the human eye to a camera. Remember how it collects and focuses light? And all of that lands on the retina. Then those amazing photoreceptor cells, the rods and cones, they convert that light into signals the brain can work with.
And that incredible power of accommodation. I mean, it's thanks to those ciliary muscles, right, and the lens that we can adjust our focus, so we can easily switch between looking at things up close and then far away. It keeps everything sharp. Exactly. And of course, this system, well, it's not perfect all the time. We talked about how, the actual structure of the eye can vary a bit, like the curvature of the cornea or the length of the eyeball. And that can lead to, those common vision problems like myopia and hypermetropia, nearsightedness and farsightedness.
Right. And we can correct those with, glasses or contacts.
Yeah.
They're kind of like mini prisms. They bend the light in just the right way to make up for those little structural differences.
For sure. And speaking of prisms, we talk about how they really reveal this fascinating phenomenon of refraction. That's when light bends as it passes from one medium to another, like air into glass. We even saw how the angle and shape of the prism change how much the light bends.
And then there's that magical moment when we connected prisms to rainbows. It's kind of mind-blowing to realize that those beautiful arcs of color are just nature's way of showing off dispersion. Those water droplets become like countless tiny prisms splitting up sunlight.
It's true. A really stunning example of, well, a simple scientific principle, just showing up in this really spectacular way. And we talked about how light's journey through the atmosphere doesn't stop there. We've got atmospheric refraction, creating those really cool, almost illusions, like the twinkling stars and the way the sun seems to change shape at sunrise and sunset.
Right. It's wild to think that those twinkling stars, they're not actually changing in brightness. It's just the light is getting bent and scattered as it goes through those layers of air. And that whole sun flattening thing at sunrise and sunset, that's just an illusion too.
Yeah.
Because the light's bending.
Exactly. It's all about perspective and how light's path gets altered as it, makes its way through the atmosphere. But let's shift gears a bit. Now let's talk about something called scattering of light. That's what makes the sky blue.
Okay, scattering of light. That sounds interesting. I know it's got something to do with the blue sky, but I'd love to hear more about the science behind it.
Well, think about, imagine sunlight streaming through a dusty room. You see those beams because the dust particles are scattering the light. They make it visible.
Ah, so the light's bouncing off those tiny particles.
Exactly. And the same thing happens in the sky. It's filled with tiny air molecules, and when sunlight hits them, it gets scattered. But here's the key. Different colors of light get scattered differently.
Wait, so some colors are easier to scatter than others?
Yep. The shorter wavelengths of light, like blue and violet, they're scattered more easily by those air molecules. The longer wavelengths, like red and orange, not so much.
So if blue and violet are scattered the most, why isn't the sky violet? Why is it blue?
Great question. Well, two things. Our eyes are actually more sensitive to blue light than violet, and the sun actually emits more blue light than violet. So that combination, that's what makes the sky look blue to us.
That makes sense. So it's not like the sky itself is blue, it's just all that scattered blue light that we're seeing.
That's it. And this whole scattering thing, it also explains why sunsets are often reddish-orange.
Oh, right. How does that work?
Well, think about it. When the sun is low on the horizon, the light has to travel through way more of the atmosphere to reach our eyes. And remember, blue light gets scattered away more easily. So as the light travels that longer path, more and more of the blue is gone, scattered out. What's left? Those longer wavelengths, like the reds and oranges, they dominate the sky.
That's so cool. So those sunset colors, they're basically what's left over after all the blue has been scattered away. Amazing.
It's true. It's a beautiful way to see how the scattering of light, and the changing position of the sun, they all work together to create these amazing displays of color.
It really makes you appreciate how complex all of this is, the light, the atmosphere, all of it. But are there other examples of light scattering, like in everyday life?
Yeah.
Stuff we might see without even realizing it.
Oh, yeah, for sure. One cool example is something called the Tyndall effect. It's named after this physicist from way back, John Tyndall. He's the one who first described it. And you've probably seen it a bunch of times without even knowing it.
Really? Like what?
Imagine those beams of light you sometimes see cutting through fog or mist. Or, you see sunbeams streaming through trees, like in a forest, illuminating all those dust particles in the air.
Yeah, I can picture that. So what's actually happening there?
Well, that's the Tyndall effect. It happens when light goes through a medium, like air, and it's got these particles in it that are big enough to scatter the light, but small enough that they stay suspended. They don't just, settle out.
So those tiny water droplets in the fog, or the dust motes in the air, they're scattering the light and making the beam visible.
Exactly. And you can see the Tyndall effect in other places too, like shine a flashlight through a glass of milk and you'll see that same kind of scattering. It's because of all the tiny fat globules in the milk.
Wow, never thought of that. It seems like this light scattering is happening everywhere. We just don't always notice it.
That's true. And this simple principle can explain, well, a ton of things. From the color of the sky, like we talked about, to how light interacts with different materials. But let's circle back to the human eye for a minute. Remember those vision problems we discussed? Myopia, hypermetropia, and presbyopia.
Yeah, those were really interesting. It's crazy how, small differences in how the eye is structured can really affect how we see.
For sure. We talked about the basics, but it's worth taking a closer look at what causes them and how we can deal with them.
Okay, I'm game. Let's start with myopia, nearsightedness. What caused that again?
Well, myopia usually happens when the eyeball is a bit longer than normal, or the cornea, that clear front part of the eye, is too curved.
So either way, the light focuses in front of the retina instead of right on it, making those distant things blurry.
Exactly. And we can fix that with concave lenses. They spread out the light rays a bit before they enter the eye, shifting that focal point back onto the retina where it should be.
So the concave lens is like counteracting the extra bending from the longer eyeball or curved cornea.
Yep, that's the idea. Now, with hypermetropia, farsightedness, it's usually the opposite situation. The eyeball is a bit shorter than usual, or the cornea is flatter.
So now the light focuses behind the retina, and things that are close up are the blurry ones.
Precisely. And to correct that, we use convex lenses. They converge the light rays, bringing the focal point forward onto the retina.
It's just amazing how we can use these lenses to, like, manipulate the light and fine-tune our vision.
It really is. It shows you the power of, understanding optics. But presbyopia, that's a bit different. It's not about the shape of the eye itself, but more about the lens, how flexible it is.
Right. Presbyopia, that's the age-related one, right? The lens stiffens up, making it harder to focus, especially for near vision.
Exactly. As we age, the proteins in the lens, they start to change, and it loses its elasticity. Those ciliary muscles, they have a harder time reshaping the lens. And remember, that's crucial for accommodation, for adjusting our focus.
So it's like the lens can't flex anymore, can't adjust its shape, and close-up things get harder to see.
That's a great way to put it. And unfortunately, presbyopia is just a natural part of aging. Pretty much everyone gets it to some degree.
So while we can't stop it, we can do something about the effects. Like reading glasses, right? They give us that extra magnification so we can see close-up things clearly again.
Right. Reading glasses are basically like magnifying lenses, making up for that reduced ability of the lens to change shape. And that way, the light from those close objects can focus on the retina properly.
It's just, it's pretty cool how we can use what we know about light and optics to come up with these, like, practical solutions for these vision challenges.
It really highlights the power of science. Understanding things can really improve our lives.
We've covered a lot today. The human eye, how light interacts with the atmosphere. But before we wrap up, I'm curious, are there any other, like, unusual or less known light phenomena that might surprise people?
That's a good question. One that comes to mind is called a glory. Have you ever been on a plane looking down at the clouds and seen this colorful halo around the plane's shadow?
Now that you mention it, yeah, I think so. It's like a circular rainbow around the shadow. How does that happen?
That's a glory. It happens when sunlight gets, we call it backscattered. It's scattered back towards the source, and that happens by tiny water droplets in the clouds. It's kind of like a rainbow. The light gets dispersed into its different colors and creates that halo.
So it's like a personal rainbow created by the sunlight, water droplets, and the person's viewpoint.
Exactly. You often see glories from higher up, like plains or mountaintops, where you're looking down on a cloud layer.
That's really cool.
Huh.
Any other unusual light stuff you can share?
Sure. Another one is it's called zodiacal light. Have you ever seen this like faint cone-shaped glow in the night sky? It extends up from the horizon, kind of along the path of the zodiac.
I don't think I have. What causes that?
Well, it's caused by sunlight scattering off these dust particles that, they basically lie in the plane of our solar system. They're leftovers from, way back when the planets and everything were forming. And they create this, like, diffuse band of light that's easiest to see after sunset or before sunrise.
So we're seeing sunlight reflecting off ancient space dust.
Exactly. It's a cool reminder of how vast our solar system is and all the stuff that's out there, even between the planets.
These phenomena are, mind-blowing. It's amazing how light can tell us so much about the world, from like the tiny details of our eyes to the vastness of space.
It really speaks to the beauty and complexity of the universe and how much we can learn by exploring it. But, let's not forget about the importance of light in our everyday lives. It's not just about these cool phenomena.
Right. Light is essential for so many things, from seeing our surroundings to, like, our mood and how we feel.
Exactly. It's vital for plants, for photosynthesis. That's how they make energy from sunlight. And it regulates our circadian rhythms, our internal clocks that control sleep, and all sorts of other things.
It's crazy to think about, light is so basic, but it's fundamental to life on Earth.
It is. And our understanding of it keeps evolving, leading to new technologies and ways of doing things that are really changing how we live and interact with the world.
So I think it's safe to say that light is, it's a lot more than meets the eye, right? It affects our world in countless ways, both big and small.
Absolutely. And the journey of discovery, it never really ends. There's always more to learn, more to explore, more to wonder about when it comes to light.
Wow. This deep dive has been, well, pretty enlightening. We've journeyed from the inner workings of our eyes to the vast expanse of the atmosphere and beyond.
It's amazing how much there is to uncover about something as seemingly simple as light, right?
Absolutely. So as we wrap up, let's take a moment to, solidify some of these key takeaways. We started by exploring the incredible design of the human eye, comparing it to, well, a high-tech camera that captures and focuses light and sends those signals to the brain, and that's what allows us to see those images.
Right. And remember that remarkable ability of the eye to adjust its focus, what we call accommodation. It's all thanks to those ciliary muscles and the flexible lens that we can so easily shift our gaze from near to far, keeping everything in focus.
And we learned that this system, while impressive, isn't perfect. We talked about those variations in the eye structure that can lead to, those common vision problems like nearsightedness and farsightedness. But the good news is we can correct those with glasses and contacts, which are basically like tiny prisms that bend light just the right way.
Exactly. And those same principles of refraction, the bending of light, led us to explore the world of prisms and how they can split white light into its individual colors. That's dispersion.
And that brought us to those stunning rainbows, nature's grand spectacle of dispersion, where water droplets act like countless miniature prisms, painting the sky with those vibrant arcs of color. It's a perfect example of how, well, a simple scientific concept can create something so breathtaking.
It truly is. But our exploration didn't stop there. We also dove into how light interacts with the Earth's atmosphere, and that's what leads to those captivating phenomena like the twinkling of stars and the sun appearing to shift at sunrise and sunset.
Right, those illusions are all thanks to atmospheric refraction, that bending of light as it travels through those different layers of air. It highlights the dynamic interplay between light and our atmosphere.
And then we explore the concept of light scattering, which explains why the sky appears blue. Those tiny air molecules scatter sunlight, and those shorter wavelengths, like blue, get scattered more effectively.
And remember those beautiful sunsets. They happen because as the sun dips lower, the light has to travel through more of the atmosphere. So more of that blue light gets scattered away, leaving those longer wavelengths, the reds and oranges, to dominate the sky.
It's a perfect example of how scattering and the changing position of the sun create those stunning displays of color.
We even had a chance to touch on some of those less common but equally fascinating light phenomena, like glories and that zodiacal light. They show us the intricate ways light interacts with water droplets and those dust particles, creating those unique scenes in the sky.
It's clear that light is much more than meets the eye, right? It's a fundamental force that shapes our world in countless ways, affecting everything from our vision and mood to the very processes that support life on Earth.
This deep dive has been truly eye-opening. I feel like I have a whole new appreciation for the beauty and complexity of light and the world around us.
It's been a pleasure exploring this with you, and to everyone listening, keep those eyes open and never stop questioning and exploring the wonders of light that are all around us every day.
Because in the grand scheme of things, light connects us all, illuminating the mysteries of the universe and revealing the beauty of this world we call home. Thanks for joining us on this illuminating deep dive.